When it comes to existential questions, whether or not we are alone in the universe is as big and important as they come. Could we be one step closer to answering it? This week, researchers at University College London announced the first discovery of water in the atmosphere of a potentially habitable super-Earth called K2-18b.
We are delighted to present you that this is the first discovery of water vapour in the atmosphere of a super-Earth in the habitable zone.
In this episode, we speak to the UCL team about their finding and ask what it means for the search for extraterrestrial life. And we talk to NASA's chief astrobiologist about the formidable challenges involved in the search for life far from our own planet, including the crucial role played by strange life here on Earth.
There is no silver bullet that says life, unless possibly we catch a glimpse of a green Martian giraffe galloping across the landscape. Pretty much not going to find that.
I'm Ian Sample, and you're listening to Science Weekly from The Guardian. Beyond the pages of science fiction, how realistic is the search for extraterrestrial life? It's a subject that challenges our ideas about what life is, while pushing technology to the limits. We'll hear about some of this a little later on. But let's start with Lewis Dartnell, an astrobiology research scientist and professor in science communication at the University of Westminster. So far, life in our solar system has only been found here on Earth, leading many scientists to turn their attention to more distant planets that orbit stars other than the Sun. I asked Lewis about the kinds of observations we can make in this area.
If we're talking about an Earth-like extrasolar planet, the principal technique is spectroscopy. We take the light from this other planet orbiting another star in the galaxy, and we effectively make a rainbow out of that light. You split it into its spectrum, and then we look for particular absorption features in that spectrum. We look for the telltale fingerprints of different gases in the planet's atmosphere, so we can effectively read the makeup of its air, the chemistry of its atmosphere. And in terms of biosignatures, one of the strongest biosignatures that we'd be looking for is a mixture of two gases in an alien planet's atmosphere. We'd be looking for oxygen mixed with methane. Because oxygen and methane are both very reactive gases, that they would be expected to react with each other to produce carbon dioxide on a very short timescale, on the timescale of a century or two. So if you see both oxygen and methane in an extrasolar planet's atmosphere, that tells you that it's out of balance, it's out of equilibrium. So some biological process has released that oxygen and methane, but more importantly, that biological process has been operating very, very recently.
And how able are we at the moment to look at these kinds of signatures in the atmospheres of planets that are actually beyond our solar system?
For Earth-like planets, so a rocky terrestrial extrasolar planet around the same mass as the Earth and orbiting a roughly Sun-like star, these sort of spectroscopic measurements are fiendishly tricky. We're right down on the detection limits, the threshold of some of the best telescopes we have around the Earth and indeed above the Earth and what we're anticipating to launch in the coming years. These are very, very difficult measurements. You're looking for a very subtle signal.
Would these biosignatures be picked up by direct measurements? Would you just be essentially pointing your telescope at the exoplanet? Or are you doing something more clever with the science, with the orbit of it?
Well, there's several different ways these sort of measurements can be made. You can, using your telescope, collect the light from both the star and its orbiting planet. And bearing in mind, of course, the star is far, far brighter than the planet around it. And if you time your two measurements well, so you get the planet as it orbits around its star, and you take a spectrum just before the planet passes behind its star in its orbit from our point of view, and then again just after the planet has been obscured behind its star, and you then effectively subtract one spectrum from the other, you can take away the spectrum from the star and leave behind the spectrum that's come from its planet. You can kind of do like a subtractive spectroscopy, if you like.
If a biosignature were found, and the kind you're talking about, a mix of oxygen and methane that suggests those gases are being produced frequently on that body, how far does that get scientists to being able to say, we think there's life there? I mean, presumably that kind of observation alone wouldn't constitute the kind of extraordinary proof someone like Carl Sagan would have said you required.
So, finding oxygen and methane in an alien Earth's atmosphere would be a very, very exciting discovery. And one of the best ways of explaining that out of equilibrium chemistry is that life has put those gases there. The only reason that you or I, and I assume a large fraction of your listeners, are all breathing oxygen at the moment, is because life has put it there. Oxygen is the pollution, is the waste gas from photosynthesis. And the Earth became oxidized about 2.4 billion years ago by cyanobacteria, by single-celled photosynthetic organisms in the ocean. But there is a caveat here, because there is a non-living, abiogenic process for putting lots of oxygen into an atmosphere as well. And this is what happened to Venus, our next-door neighbour planet. And if a planet is too close to its star, it gets too hot as the star heats up, as it matures, any oceans on the surface of that inner world boil away into steam in the atmosphere, and that H2O is then split into hydrogen, which escapes because it's a very light gas, and oxygen, which stays behind a bit longer. So you can get an oxygen-rich atmosphere not through life, but effectively as the planet dies, as it boils itself dry. So let's say in 20 years' time we've used our telescopes and we've got 10 nearby Earth-like planets that have all got oxygen in their atmosphere. We would know that the majority of those are probably due to life, but we couldn't say with absolute certainty that any one of them has life on its surface because of this oxygen signature. We might have just so happened to have catched a planet as it undergoes this Venus-like runaway greenhouse effect.
And are there things that you can look for in an atmosphere that would say, you know what, there's no chance you're going to get life on this planet. It's just either too toxic or too something, that there are signatures which will say, look, the chances are really low here?
Yeah, so most of the time, astrobiologists focus on atmospheric biosignatures. What gases are released by life, and therefore we can use them as a telltale fingerprint or signature in an exoplanet. But just as interesting, just as informative, are what are known as anti-biosignatures. What gases might we detect in an exoplanet that would indicate, in fact, that there isn't life there? And one good example of an anti-biosignature would be something like carbon monoxide. Now, we know carbon monoxide to be toxic to human life, and indeed other mammals and vertebrate animals, because it effectively blocks hemoglobin. Carbon monoxide binds to hemoglobin and stops you then being able to transport oxygen around your body, so you effectively suffocate. It's not for that reason. Plenty of bacteria obviously don't have hemoglobin in bloodstreams. They're not poisoned by carbon monoxide in that sense. And the reason is much more to do with the fact that carbon monoxide is a very energy-rich gas. And if we find, therefore, carbon monoxide in a planet's atmosphere, it tells us that no one's eating it, that there's this very available, energy-rich source of nutrition on the planet, but no life seems to be exploiting that. And therefore, that would indicate that probably there's not life there at all.
That was Lewis Dartnell. This week, University College London released the exciting news that they've detected water in the atmosphere of a potentially habitable planet 110 light-years away. One of the team is Professor Giovanna Tinetti from UCL's Centre for Space Exoplanet Data, and I asked her to tell us about the super-Earth they've been looking at.
It's a planet that is 8 times the mass of the Earth and is called K2-18b. And this planet is orbiting a star that is colder from our own Sun, and so also slightly closer to this particular star. What is quite interesting about the super-Earth is that the distance to the star makes the planet in the habitable zone of the star, which means that is a good distance from the star, so that is not too hot, is not too cold, and in principle you could have liquid water on the surface if there is a surface, and of course if the conditions are permitting that.
And how far away is the planet? Do we know what constellation it's in, or give us some sense of where it is in the sky?
So for the moment, most of the planets that we're looking at are, in a certain sense, in the solar neighborhood. Of course, 100 light years away, it doesn't seem like so close, but in terms of galactic scale, it's really, really close by. So it's still far away, too far away to get there, but it's in a certain sense, again, in galactic scales, it's quite close by.
And I think it's in the constellation of Leo. Is that right?
Correct, yes.
So what is the thinking? That it's a lump of rock, or that it's a ball of ice, or where are you on what the composition is?
So, of course, the density per se is just one parameter to define a planet. And so, of course, you need to know much more in order to understand, what does it mean, the density. So the density is enough to tell you it's something that presumably has an interior that is a mixture of rocky and ices, given that it's slightly lighter than the density of the Earth or Venus, but again, as I said, more similar to the moons of the giant planets. But then, of course, you need to do measurements of the atmospheric composition, understanding, first of all, whether there is an atmosphere or not, to go beyond that it's just one number giving you the density.
And you were looking specifically at the atmosphere of K2-18b. Why was the atmosphere so interesting?
Well, we are very interested in general about the atmosphere of these exosolar planets because these are the gaseous envelope, which is the atmosphere, is the only part of the planet that in principle you can observe directly. Unfortunately, we can't really send a probe to these planets, they're too far away, so you can't dig into the planets like we're doing in our own solar system for many objects in our own solar system, so we can't do that. But given that the atmosphere is made of gas, gas can be transparent to some type of lights, and so you can use basically this information to find out what is the chemical composition of the atmosphere, and through that then you can understand also the chemical composition of the planets in its bulk.
So you used Hubble observations to look at the atmosphere, is that right?
Yes, that's correct. Hubble at the moment is basically the only instrument that we have up in space that is able to tell us something about the chemical composition of these atmospheres. It's not perfect for many reasons. It's a relatively old instrument. It's great that it's still there and it's still giving us fantastic measurements. And also, in principle, we like to look at different type of lights, so moving a bit more towards the infrared compared to what we can do with Hubble. But that's already great what we can do with that, and the glimpses we can get out of those atmosphere really gives us a lot of appetite for future observation with more performing instruments.
So what do you find?
Well, to our a great surprise because you never know what you're going to find, and the more you do models to predict, the more typically these models are not really correct. To our surprise, we could see a pretty strong signature water vapor. That means that, first of all, there is an atmosphere on top of that planet, and again, being a super Earth is not given. You could even have a bare planet. But there is an atmosphere, and there is an atmosphere that contains a significant amount of water vapor. And that is quite amazing, given that this is a planet, again, in the habitable zone. And certainly water is one of the ingredients that we put in the list for a planet to be habitable.
So is this a first in any way?
It is. It is a first. And also through this observation, you can also estimate quite well out of the observation the temperature. Because normally if you don't have this atmospheric measurements, you estimate the temperature in a certain sense by a little bit of a guess, because you work out how far is the planet from the star, and then you do some models to estimate roughly what is the expected temperature. But this estimate is very approximated. Through this measurement, we could also constrain much more the temperature of the planet, which is really spot on in the habitable zone. It's really not very far away from the one on the Earth.
What does this mean for the habitability of the planet? I mean, do we even know what life needs in an atmosphere?
That's absolutely a great question, because for the moment, the only example of inhabited planet we have is the Earth, and that's it. And we tend, as scientists, to extrapolate out of the Earth, but it's a very geocentric view, as you can understand. And so we need, for sure, to have similar observation for more and more of planets in the so-called habitable zone, to understand, first of all, whether that habitable zone really is a good indicator of habitable condition or not. But most importantly, this particular planet is not Earth 2.0. It's in a certain sense a cousin of the Earth. It's not really the twin. It's heavier to start with, and on top of water vapor, there are some indication that there is still hosting some hydrogen. So clearly the atmospheric composition is not the same of the Earth. And so what does it mean for life? I mean, of course, there are a lot of models and debates in the scientific community, and in principle, being heavier, still containing some hydrogen, is not a big problem for life. You can have life even on Earth. They're absolutely fine with this kind of parameters. But of course, it means that we need to understand a little bit more about habitable conditions, especially when we're looking at planets that, again, are cousins of the Earth, not exactly the Earth's twin.
So what is next for your team? Are you going to be looking more at K2-18b, or are you going to move on to other exoplanets to look at their atmospheres?
I think all of the above, because, of course, this turns out to be an incredible planet to look at, and you don't know in the beginning when you make the observation. In some cases, you have targets that are extremely promising, and then you look at the observations and you can't extract anything for a number of reasons. And in other cases, you wouldn't put your bet on that planet, and then it turns out that there are unexpected surprises. So I think we definitely need to look at more planets in general, but this one in particular needs to be observed more and more with different telescopes.
Giovanna Tonetti. After the break, we'll talk to NASA's chief astrobiologist about the US Space Agency's latest work in the search for extraterrestrial life, and how Earth's most hostile environments and the life found in them are a valuable guide. Welcome back to Science Weekly. Before the break, we heard about the exciting detection of water vapour in the atmosphere of a super-Earth. It's the first time water has been spotted on a planet in its star's so-called habitable zone, where the temperature is just right for running water to exist. But if we think about taking it one step further and looking for life forms, what kind of techniques are on offer for that? Dr. Penelope Boston is the director of the NASA Astrobiology Institute, the NAI, at NASA's Ames Research Center in California. She's also an expert on subsurface environments like caves and mines, some of the most extreme physical and chemical environments on Earth. In places like these, scientists find life even though photosynthesis is impossible. I started by asking Penny about the imaginative leap required when we think about extraterrestrial life. How do we have to rethink what we've learned from observing life on Earth?
That's a very interesting thing. It's a tricky line to walk because, the last 50 years we have learned such a tremendous amount about life on Earth. We've learned how to look at our genetics of ourselves and other organisms. We've learned much about the way the ecosystems on Earth work. We've learned a lot about the deep time history of our planet and its many changes over the 4 billion years or so that the planet has been in existence, and the probably 3.5 billion to 3.8 billion years that we have a rock record of some sort of life being present on the planet. This is a wealth of information. On the other hand, we're looking to find life on other bodies, both in our solar system and beyond, that have potentially very different properties from Earth. Some are described, of course, often as Earth-like around other stars, but the only thing we currently mean by that is that it's a planet that is close enough to its star to be warm enough for the presence of liquid water. And our grasp of what Earth-like means in terms of these exoplanets is still very, very much in its infancy. And so trying to take what we have learned from these many decades of study, in fact, hundreds of years of study of life on our own planet, and then try to take the fundamental messages that we get out of that and then reapply those in a novel way, but a realistic way, to these very different exotic bodies in our own solar system and beyond is really a very challenging intellectual exercise, but it's a whole lot of fun.
Why is it so important to understand how life exists in these really extreme environments on Earth?
You know, the extreme environments on Earth are compelling for several different reasons. One of the main ones is because we're actually able to see how our type of life is pushing up against the envelope of what it can do. The temperature ranges and the chemical extremes, the saltiness or the presence of heavy metals or the presence of very cold temperatures, acidity, or the opposite of that, alkalinity. All of these factors, life on Earth has been able to accommodate. And so we're trying to expand our understanding of how big that bubble is that encompasses what life can do here, and then to try to learn the fundamental lessons from that about what our kind of life can do, and try to apply that as we look at other bodies in the solar system and beyond.
When it comes to searching for life, how does it differ if you're looking for living organisms as opposed to signs of past life?
You know, that's a great question, and it's one that we spend a lot of time thinking about and trying to discern how we do that. I'm imagining that a lot of folks have never hunted fossils on Earth, although some of the listeners may have. And if you have any experience with that, you know that's very different from bird watching. So it is a largely rock-based enterprise. We're looking for signs of previous activity, and sometimes you find whole fossils like wonderful dinosaurs and so forth, but for the most part, we're looking for much more subtle signals. So we're looking for the chemistry changes that life makes in the environment in which it once lived. It can take chemistry and not only change the chemistry itself, but also change the isotope number of the elements within those chemicals. So, for example, carbon, which, as we know, is so important, we're largely made out of carbon, is one of the main constituents that make up the molecules in our bodies. Those carbons can be sorted depending on how heavy they are. So there are lighter and heavier versions of carbon, just like there are other elements, and life prefers the lighter ones. And so on this planet, we know that, and so we can try to track the lightness of the carbon or the heaviness of the carbon. The same thing is true of sulfur, even nitrogen, and we can get climate signal from looking at the heaviness of oxygen atoms of different weights. And so some of the evidence is, potentially very visual, that is, biotextures that microbes can create as they're living, which get preserved in stone, all the way to these very subtle chemical indicators.
There are challenges all over the place when it comes to doing this kind of science, and one you've talked about before is this need to take simultaneous measurements. Can you just walk us through that? Why is that necessary?
Well, in the extreme environments on Earth, one of the things that we have learned is that the organization of the organisms is very patchy. So if I look at a very rich environment, like if I were going to swab your throat for strep organisms, right? If you had a sore throat, and I would plate that out on an agar plate, and those organisms would appear everywhere because they're used to lots of food. The food could be you, and when I swab it onto a plate, then the food is what I've put in the plate, and so we see a lot of growth. But in these very low nutrient environments where organisms have to work very, very hard, they're not evenly distributed. They're in little clumps, and sometimes those little clumps are centered around extra rich bits of nutrient, but in many cases, the forces which enable them to array themselves in the environment are not real clear to us. They seem to have some potential properties of self-organization, which is something that we really don't understand very well yet. And so we're looking for needles in haystacks, trying to second guess where those needles might find themselves. We have to look at these environments not just in the bulk properties of what we can easily measure by scooping up large amounts of stuff, but how do we actually look for these very tiny, potentially tiny, very discrete places where we have organisms. And this means that we need to employ a lot of different ways of trying to sense that as we look at the environment, and we need to look at it at the scales at which these types of organisms live. And, we do have spectacular large deposits of minerals on Earth that are clearly influenced heavily and in some cases produced by the presence of the microorganisms. So in those cases, we have big eyeball-sized things that we can look at. But in many cases, we don't see that. If you look at your feet and look at a bare patch of soil, that's teeming with microorganisms, but to your eye, you don't see any of them. And so we have to go down to smaller scales and chemical means to actually try to figure out who's there and what are they doing. And when you're in an environment with very little free energy for those organisms to live, the problem of finding them becomes very, very much greater. And so that's what we're trying to tackle, because we assume that in many of the bodies in our solar system, particularly places like Mars, that life that we may find there may be very, very, very isolated in little patches.
Another issue, I think, is the duration of missions. Is it right that the missions typically don't last very long, and that itself can be a problem?
Yes, that is definitely one of the limitations that we have been up against. Many people in the communities relevant to this, both the technology and the science, are thinking about how we can work our way forward towards longer-term monitoring of environments. And I think this is definitely one of my pet subjects, because the work that I've done on Earth in the subsurface in caves and mines, and the organisms that we've been able to actually grow and keep going in the lab, many cases take many, many years to even show that they're growing. And so I know the value, as do many of my colleagues who work in similar environments with organisms that are very, very slow to change and do anything, that, a quick snapshot is only giving us a glimpse of what we ultimately want to interrogate. And so, of course, we certainly have aspirations for eventual human presence on Mars, and one of the things that astronauts can be imagined to be doing in the future is actually, continuing the search for life on Mars if we have not uncovered it by the time we actually get ready to send humans.
A lot of the chemistry that has to be done on planets and other bodies to look for, say, biosignatures, biomarkers, it seems to be incredibly sensitive. And so when we're talking about robots, there's presumably always this risk that you've carried something with you from Earth, that you have some microbes on board already, that will always be in the back of your mind. Have I actually just analysed something I took with me? How does an agency like NASA deal with that potential risk?
Well, we take it tremendously seriously, and this has a hugely long history. The first discussions about how we protect life that we may find on other planets, how we don't mistake Earth life for that life, and how we also protect our own home planet against the possibility of bringing something deleterious back from another planet when we get to the point where we're actually bringing samples back from some of these bodies. It has occupied us for the whole history of NASA. The first discussions of this started in the late 1950s, which was the time at which NASA was created, and the space age was just starting. We have a planetary protection office within NASA that deals with this. There are stringent guidelines for different bodies. So, for example, the moon, we are quite confident that the moon does not and has not housed intrinsic life. It may have received splashes of Earth life, from the past, but it doesn't have an indigenous life process going on. And so the requirements for moon are documentation, careful documentation, because, we're scientists and engineers, we document everything. And so we want to know what Earth organisms we may be taking as we are ramping up along with other space agencies to return to the moon. But very sensitive objects like Mars landing are some of the most sensitive, stringent requirements that we have for reducing what's known as the bioburden, which is just a terminology way of saying how many bugs do you have on board, how many microbes do you have on board, and what is the acceptable level of those. One of the good things that's on our side for surface landing Mars missions is that the Mars environment on the surface is so extremely hostile itself that there is some, help in terms of the very, very dry conditions and the high ionizing radiation and the high ultraviolet levels that fall on spacecraft when they're on the surface. But that doesn't mean that we send them dirty. We send them very, very clean, and we send them with a very, very low amount of buried biological contents. We're facing challenges now as we're thinking into the mid to far term range about how are we going to look at things below the surface of Mars. That's one of my own personal particular interests, and this is an idea that has been gaining traction slowly within the agency and elsewhere, because we know that the subsurface of a planet like Earth and presumably Mars is very different from the surface, and we want to be able to study that. But because it may be a more promising place on the planet for life, we have to then be extra careful as we go forward to try to protect that.
I'm wondering, Penny, if you have a sort of future gaze and think about where the first signs, the first convincing signs might come from, whether you think those will come from these people looking way beyond our own solar system, or whether the solar system itself looks very promising to you. And I know NASA has another rover going back to Mars, yes, I think next year or the year after.
Yes, very soon.
But people also talk about places like Enceladus and Europa and, these interesting moons of some of the further out planets. How do you rank these, I suppose?
I am such a space cadet that I love them all, and I have a bet with a friend of mine, Seth Shostak, who is a specialist in SETI, which is a search for extraterrestrial intelligence, which is something that we're not directly working on in NASA, but of course most of us are quite interested in it. My bet with him is that we're likely to find signs of life, not necessarily intelligent life, but signs of life on an exoplanet before we nail it down here in our own solar system. And my reasoning for that is that we're finding more and more and more and more and more exoplanets. And so it's a numbers game. And even though the quality of the data is so much more restricted than what we can gain in our own solar system, we don't have to work as hard for it. And it's a big galaxy. So I sort of think that we may see tantalizing signs in the atmospheres, particularly when some of the new generation telescopes start coming on board. As I'm sure you're aware, we've got a big one that we're working on here, the James Webb Space Telescope, which is going to be launching soon. I won't put a date on it, but that's a huge project, and that is a very capable instrument, some of whose time will be spent on this exoplanet issue. There are many other ideas that are competing within NASA and also within ESA and other agencies for telescopes that are even more refined in terms of their ability to let us look at exoplanets. So I think it's a race to the finish. The work that I have done personally obviously pertains directly to our search for life here in this solar system. But of course, the global scale of what life does to a planet is something of equal interest, perhaps even greater interest. And so that's what we're trying to apply. So I'm kind of betting on the exoplanets, but working as hard as I can to defeat my own bet and hope that we find stuff in our own solar system as soon as possible. I
presume also that this search never really ends, does it?
No. If tomorrow we, stumbled across something with our Mars landers that are there now and thought it was a strong evidence of life, we'd want to go back immediately to test it more. And then we'd be so thrilled that would galvanize us even more to want to go look in places like Enceladus and Europa. And maybe even for prebiotic conditions on places like Titan, the giant dense atmosphere moon around Saturn, maybe Pluto, which we now know is an active little amazing world. So the more you find, the more you hunger to find more.
A big thank you to Penelope Boston for joining us from NASA's Ames Research Center in California's Silicon Valley. Thanks too to Giovanna Tinetti and Dr. Lewis Dartnell for joining us. And you can find out more about their work on the episode page of the podcast. But for now, until next time, goodbye.
For more great podcasts from The Guardian, just go to theguardian.com/podcasts.